So today's lecture is about this concept or this procedure called Graham-Schmidt orthogonalization. It's a fairly simple and straightforward concept. I don't think they even deserve their name over here. It's that simple. So what this is about? So recall that if we have n orthogonal vectors, any number of orthogonal vectors, then they are automatically linearly independent. So n orthogonal vectors are linearly independent. If you know they are orthogonal, they are automatically linearly independent. You don't need to check anything else. And if you are talking about if they happen to be in an n-dimensional space, in n-dimensional space, they will form a basis. Because just a reminder, n linearly independent vectors in an n-dimensional space form a basis. If you can just collect n linearly independent vectors, you already know that there will be basis. And if you have n orthogonal vectors, then they are linearly independent. And since they are n, so they form a basis. And this kind of basis, we studied them last time. This is called an orthogonal basis, where all vectors are mutually orthogonal. And on top, if they also happen to have, so in this basis, if you have these two vectors, the scalar power is 0 if I is not equal to j. And on top, if you also have this condition that if you are making the scalar part of a vector with itself, that gives you the norm square. If this is 1, then this is also normalized, and such a basis is called orthonormal basis. And we like these orthonormal bases because they are easy to deal with, since finding the coefficients of any vector in this basis is very easy. If you have a vector like this, written in this basis as this linear combination, where these vectors are the orthonormal basis vectors, then the ith coefficient, all you need to do is compute this scalar product of the vector with the ith basis vector, and that gives you the coefficient in the expansion. Now, this is if you are given an orthonormal basis. How does it look like? If I consider geometrically, these basis vectors are like this. Or if you want to rotate, something like this. But this will not be an orthonormal basis because there is an angle which is less than 90. So this was if you are given an orthonormal basis. What if you are given a basis which is not orthonormal? This Graham-Schmidt procedure tells you how to get, starting from this non-orthonormal basis, how to get an orthonormal basis. You can always do it, and this Graham-Schmidt procedure tells you how to do it. So let's just go over what is this procedure. So suppose you have a basis at your hand, and the basis vectors are x1, x2 up to xn, because you are in a n-dimensional space. And they are not necessarily orthonormal. So we don't necessarily have these two. If I take two different ones, then this is not zero. So they are something like this, these kind of vectors. And the length of each one of them individually may not be one. So they are completely general basis. You are given a completely general basis with no assumption about their scalar products. Now, starting from this, you can get an orthonormal basis by doing this process. So let's run the Graham-Schmidt procedure. Which will generate for me, starting from this basis, an orthonormal basis. So what do you do? So you pick the first vector. Which one is the first? It doesn't matter. You can just number them, order them in any way you like. Once you have an ordering, just pick one of them, and the first you pick, I'm just calling it the first one. Pick the first vector x1, and since we are not guaranteed that it's normalized, you just normalize it by hand. How do you do that? You define a new vector which is just obtained by taking this x1 and dividing it by its norm. This will make it normalized. So this is just a reminder. If you divide a vector by its norm, the resulting vector has norm 1. So fairly intuitive. You had some length, you divided by that length, so the remaining length becomes 1. But you can check it. Let's check it for the one which we defined. So if I compute the scalar product with itself, which gives me the norm square, but in this case, it will become, since I have divided by norm, norm is just a number. So since it's a number, and I know that the scalar product is linear, so I can bring out both of these numbers out. So I bring both of these out, that becomes a square. And this is the definition of norm square. The scalar product of vector with itself, that's the norm square. That's just the name of the norm square. So that means, since I had divided by the norm, my resulting vector has a norm 1. That's what we have proved. So now I have got the first vector, which is normalized. Now I want a vector which is orthogonal to this. Orthogonal or normal to this, to U1. I've got the first vector in my new basis which I am constructing. I need the second one. So how do I get this, starting from what I already have? Well, we know that if you have this u1, it was in the beginning, it was x1. I adjusted its length to make it a normalized one. And then I have this x1 pointing in some random direction, and their angle, their dot product is not zero. They're not orthogonal. But we did it last time that if I consider its projection, and let's call it P1, that's the projection of U1 onto P1, then this vector, which is going straight up, this would be orthogonal to U1 from this figure. This gives us an idea how to define this vector. And this vector is simply, so this is not x1, this is x2. This was the x1 with adjusted length. So this would be simply x2 minus p1, because p1 plus, by head to tail rule, p1 plus x2 minus p1 is going to give me x2, this. They cancel and you get x2. So this must be x2 minus p1. And it's obvious that it should be, it's giving me an idea that this should be orthogonal to u1. So using this, we define, we construct, first we construct this P1, which is the projection of x2 onto u1. So how do I get it? Scalar product of x2, this is x2, with u1, and in the direction of u1. And then you divide it by the norm square of u1. Because you get a norm from this scalar product, you get a norm with this direction. So you cancel both those norms to get the component of x2 along u1 and with the direction of u1. So this is how we define the projection. But in any case, if I define it, if I just construct this vector, you will just see from algebra that it does the job for me. But this is vector projection of x2 onto u1. And then I define, construct this guy. And let me give it a name, u2 hat vector. And it is x2 minus this projection. Now my expectation is that this vector I have constructed is going to be orthogonal to the first vector u1. That was the whole point of doing it. And you can check. So I just replace this over here. I get x2 minus p1 with u1. I know that the scalar product breaks up. And instead of, for p1, I put that thing. And I know that the numbers, these are numbers, because it's already a scalar product, so it's a number. Numbers come out. And this vector is then put inside the scalar product with the vector with which you are making the product. So they cancel. Well, actually, I didn't even need this u1 because u1 was already normalized. So this was actually equal to 1. But it doesn't matter, it cancels anyway. So I get this. So which is 0 because they are same. So I have constructed a vector which is orthogonal to the u1, the first one. But I don't know if it's normalized or not. So you simply normalize it. Normalize u2 by defining this u2 vector, which is now your required second vector in your basis. So this is simply divided by the norm. Now, just a reminder that when you scale a vector, like I have done over here, change its scaling, change its norm by multiplying by a number, that doesn't destroy its orthogonality with other vectors. Reminder, multiplying by a number, like I have done over here, multiplying and dividing is same thing, does not change orthogonality. So let me just quickly, as a practice of dealing with these objects, show it. So if you have two vectors v1 and v2 which are orthogonal, that means the scalar product is 0. If I multiply v1 by alpha and v2 by, let's say, beta, any numbers which are not 0, then by the properties of scalar product, these alpha and beta come out. And I know that this is the condition v1, v2 is 0. So alpha beta times 0 is just 0. So that means scaling it doesn't destroy the orthogonality. So that means I had constructed u2 had to be orthogonal, then u2 is also orthogonal to u1. So now I have got these two vectors which have these properties. The norms are 1 and the scalar product with each other is 0. So this was the u1. I got some u2 hat which was orthogonal. Then I scaled it to make it unit, having unit norm. That scaling does not change the scalar product, which is about the angle. Now this u1 and u2, they belong to the span of x1 and x2. Because what is u1 is just a multiple of x1. And what is u2 is constructed out of u1 and x2. If I go back here, so what is p1? It's some u1 multiplied by some number, and u1 is x1 multiplied by some number, and u2 is x2 minus x1 multiplied by some number. So it's a linear combination of x1 and x2. They both are a linear combination of x1 and x2, so they live in the span of x1 and x2. But I can make a span of any two vectors. So if I make a span of u1 and u2, since these are linearly independent, this is two-dimensional, this space, span of x1 and x2. Because they were linearly independent, because x1 and x2 were part of a basis, so they were linearly independent. So if I make a span, they act like a basis for that subspace. And since I have these two vectors in that basis, so it's a two-dimensional subspace which they span. But span of u1 and u2, because u1 and u2 are linearly independent, so it's going to span the same space. So they also, because they are linearly independent, so they also form a basis for two-dimensional space, subspace. So that means this span is same as this span. So it's something like this. If I think of it pictorially, I had something like this, x1 and x2 in the plane, and this span, because the whole plane, because they are linearly independent. What I did, I first scaled x1 to make u1, and then combined these two to make u2. And since I have got in the same plane two linearly independent vectors, so they still span the whole plane. They still form a basis, but the nice thing is that it's now an orthogonal basis. So you've got two, you keep moving. Now I want the third one. So now you move on to the next vector. And what's the job? Find the third vector, a third vector, which is perpendicular to both first and the second. First and second that you have constructed. Which ones you have constructed? These u1 and u2. So again, the idea is that I'm going to consider the projection of this third vector x3. So now you have this u1 and u2. This x3 is not within this plane because it's linearly independent. So it's sticking out a little bit, but we don't know if it's like exactly perpendicular or not. So it's sticking out somehow like that. So what you do, you construct its projection onto this plane. And when you subtract this projection, then you know that you will be left with something totally perpendicular. So that's the idea, but we can do the algebra and construct it explicitly. So you define in the same manner as before this projection. You want to make sure that this projection is, when I will subtract it, it should be perpendicular to both u1 and u2. So you define it this way. Since it's the projection of the x3 vector, so x3 comes here, projection along u1 and in u1's direction. I don't have to divide by norm. In principle, I should be dividing by norm, but norm is 1, so I don't care. It will just give me 1. Right? In principle, I should be doing, but this is 1 because they are already normalized. So I don't need to write it. It will just save me some space over here. Now you form, just like before, a new vector, which is you take x3, this one, and from this you subtract the projection inside your previous plane. So this thing which you have constructed, you just subtract it out. And now you can check. So these pictures give you idea. They are not a proof, but we can prove these things. Now the claim is that this thing which I have constructed is perpendicular to both u1 and u2. That's the claim, and now we can check it. So this is the thing which we have constructed. With u1, I get x3. I'm just making it directly. u1 minus the number comes out, and you get u1. It had two. Let me just move it a little bit up. It had two of these. So first this number comes out and you have a scalar product of u1 with this guy. Then this number comes out and you have a scalar product of u1 with this guy. So x3, u2 comes out, and you have a scalar product of u2 with u1. See, I am taking the scalar product of u1 with this guy. So once u1 hits it and gives you this, and then it hits this guy, which is this. So once you make a scalar product with u1 over here, and once with this u2, and these numbers, they just come out over here. But if you look over here, it's a scalar product of u2 and u1, and we already constructed so that these are orthogonal to each other. So this is 0, and u1 is normalized, so this is 1. So you get so they are same, so this is 0. So you find that this is orthogonal to u1. Similarly, you can check with u2. Same thing goes. u1, and this time the only difference is first you have u2 and then you have u2. So again, since they are orthogonal, this is 0 and this is 1. Yeah, this survives. So they are equal and you get a 0. So you have constructed a third vector which is perpendicular to both, and all you need to do is just normalize it. And you got your third normalized vector. It is a norm 1 and is orthogonal to the other two. So now we have got three vectors. Three vectors which are mutually orthogonal and normalized. And by same logic as before, since they belong to the span of x1, x2, and x3. I didn't use anything else. I just made linear combinations of x1, x2, and x3. So they live in this. So their own span is also same because they are orthogonal, so they are linearly independent. So they will, this is a three-dimensional space. If you find in this space any three linearly independent vectors, so these are our basic theorems. You should be, by now, you should have memorized these. You have this three-dimensional subspace, so any three linearly independent vector in this subspace will form a basis for it. So their span will be the whole space. So we have got these three orthogonal vectors, and I know, as I said in the start of the class, any orthogonal vectors are linearly independent. So you got three linearly independent vectors, so they are also a basis. So these things are same. So what we are doing is, one by one, we are constructing the orthonormal basis. We are increasing it one by one. And at each step, we construct a bigger and bigger subspace of the full space. So keep going. And finally, you will have the full space. You will have n vectors. Keep going, repeat the process. Let me just give you one, I'll not prove, but let me write. How will you write the next one? You construct this. Take the x4, make its projection along u1 plus its projection along u2 plus its projection along u3. Then define this u4 as difference of x4 minus this projection. So once you take out this projection, the resulting vector is perpendicular to all these. So this will give you, and then you just do this. Just divide by the norm, and then u4 will have norm 1 and its scalar product with all of these will be 0. So you can keep including one more, and finally you will have a completely orthonormal basis starting from any basis. So this is a very useful process. If you want to deal with orthonormal basis, then one can run this and starting from an ordinary basis get an orthonormal one. Actually, when you are introduced vector spaces in high school, you are usually introduced with these guys, I, J, K, this basis, which is an orthonormal basis. So you are more familiar with orthonormal basis. Later you realize that these kind of vectors, they are also perfectly capable of generating the whole space. It's just that they are not very convenient sometimes because they are not orthonormal. So let's take an example of running this process explicitly. So consider this basis. In R3, you're just told that it's a basis in R3, you can very quickly check. All you have to check is if they are linearly independent or not. And if you are in R3 and you're checking three vectors to be linearly independent or not, there's a very easy way. You just compute the determinant of the matrix. And if this is not zero, then they are linearly independent. I'm not going to do it. I'm just take my word that these are linearly independent. So they form a basis. Now let's run this process. So I take this, and the first step is that you normalize it. To do that, you compute its length. Length you can compute by just squaring each component, because in principle, length is square root of the vector of the scalar product of vector with itself. And how do you compute the scalar product? Take the corresponding components of the two vectors, which in this case are same. So the corresponding components just get squared. So this gives me 1 plus 4 plus 4, which is 3. So therefore, the first vector in my new basis is going to be this original vector scaled by 1 over 3. So it's this vector. And you can obviously check that its length square is 9, 1 plus 4 plus 4, 1. Now in the next step, that's what I have to do. Just a reminder again. I've got this was some x1. I scaled it, made it u1, and I have this x2. Now I compute its projection, p1, and then construct this perpendicular component, which is just x2 minus p1. And this will be my orthogonal vector which I'm looking for. So p1 is simply u1 x2 u1. You write x2 this way, this side or that side, we know that it's symmetric, doesn't matter. And I don't have to divide by u1 u1 because the norm is already 1. So we have to compute u1 x1 x2. So now u1 components are, we have to multiply the corresponding components and add. u2 was, x2 is given here, 4, 3, 2. So I get 4 plus 2 by 3, 3 minus 2 by 3, 2. Because x2, let me just write over here, was 4, 3, 2. So the scalar product becomes so it's 3, 4 plus 6 minus 4. So 6 over 3 is 2. Therefore, this P1 is 2 times U1. And U1 is written over here. So it just becomes 2 over 3, 4 over 3, and minus 4 over 3. Let me just show you U1. So it was 1 over 3, 2 over 3, minus 2 over 3. I just multiplied by 2. That means each component has to be multiplied by 2. Then I have to compute this difference. To construct this U2 in my Gram-Schmidt process, take x2 and subtract from it this projection along x1. So x2 is this, and p1 is this. So this vector becomes, when I subtract, I have 12 minus 2, 10, and 9 minus 4, 5 over 3, and 6 minus 4, 6 plus 4, because there's a negative here and negative outside. So it's 10 by 3. So this vector, it better be perpendicular to U1. And we can check. So U1, it was, the first component was 1 over 3. Its first component is 10 over 3 plus 2 over 3 into 5 over 3. And U1's first component, third component was minus 2 over 3. Three times 10 over 3. So I get 10, 9, 10 plus 10 minus 20. So it is 0. And now I want it to be normalized as well. So I compute the norm of this guy. This guy. So square and add each component. So I have 225 over 9, which is 15 over 3. So it's 5. So I get my normalized vector by dividing this U2 hat by 5. This guy by 5. So I'm going to have 2 by 3, 1 by 3, and 2 by 3. So this is my vector. And you can check again just for more reassurance that scaling does not destroy the orthogonality. So this is U2, and U1 was, let me just copy. U1 was 1 by 3, 2 by 3, minus 2 by 3. So when I do this, I get, this goes with this 2 by 9 plus 2 by 9 minus these two 4 by 9. So it is 0. And you can check also U1, I think we already checked that U1 norm is, if, let me quickly do it, 1 over 9 plus 4 over 9 plus 4 over 9, 1, and U2 norm square, but if you will take the square root, you will still get, because it's 1, you will still get 1. So 4 over 9 plus 1 over 9 plus 4 over 9 is 1. Now we want the third one. We have constructed two vectors which are normalized and orthogonal to each other. Now you get the third one, and to get the third, first you have to construct the projection of x3 along these two guys, along U1 and U2. So this was the prescription of Graham-Schmidt to do this. So I'm just running that. And U1 x3 is 1 by 3 times 1. Let's write what was x3. x3 was 1, 2, 1. Wait. And U1 is 1 by 3, 2 by 3 minus 2 by 3. So plus 2 by 3 into 2, 4 by 3 minus 2 by 3. So it's 5 minus 2 is 1. And U1, U2 scalar product with x3 is 2 by 3 times 1 plus 1 by 3 times 2. The only difference was the third component was positive. So it's 2 plus 2 plus 1 over 3 is 5 over 3. So P2 would be x3 you had to, U1 you had to scale by this number you got here, but that was 1. So over here you just get the U1, and you have to add to it U2 but multiplied by 5 over 3. So U2 was 2 by 3, 1 by 3, 2 by 3. So you get 10 by 9, 5 by 9, and 10 by 9. And this gives you 9, and 3 plus 10, 13. 11 by 9, and minus 6 plus 10, 4. 4 by 9. Then you do this. The next step, that subtract this projection from the vector itself. So you get 1, 2, 1 minus 13 by 9, 11 by 9, 4 by 9. So you get minus 4 by 9, 18 minus 11, 7 by 9, and 9 minus 4, 5 by 9. So you have U3, you have constructed it, and you can check its projection. You get -4, 9 by 3, 9 into 3, plus 14, 9 into 3, minus 10, 9 into 3, which is 0. And you can check with the U2 as well, but you can normalize it to get your normal vector, which is orthogonal to the other two. When you normalize it, you get nine square. So you got 9 square and 49 and 25 is 64. 64, no, 74, right? 74, 80, 90. So it's 9 into 10, 9 square is 10 over 9. So you just have to divide by this number to make it normalize. And this way you would have constructed the full orthogonal basis. So any question? So let me move on to the next topic. We will study it in more detail next time, but since we have time, I thought I will be done by the time I have done this example, but we have a lot of time available. So let's start discussing the next topic. So these are called the eigenvalues of a matrix. So suppose you have n by n. N by n matrix. So that means if I multiply it from the left by to an n column vector, it will give me back an n column vector, right? Because it's a n by n. But suppose if I choose find a vector, or maybe in other words you can say, if for a vector for eigenvectors, what symbol should I use? Let's just use V. If for a vector V, you have that A times V, when you act on it, you get V back, but maybe multiplied with some number. If this happens, then you say, it's a definition, you say V is an eigenvector of A. And you say that lambda is an eigenvalue of A. Now, when will this happen? So in general, usually what you are given in many problems, we will look at many applications of what we have been discussing. We have kind of stopped on applications, but we will turn back to applications. This is pretty much our last topic. And then for the rest of the 10 lectures, we will be doing applications. So you will see that in many applications, what you are after is that you are given a matrix, a square matrix, and you want to find if there are eigenvectors for it. And if they are, what are those eigenvectors and what are the eigenvalues? So how can you find them? So I assume that there's some eigenvector like this exists. This is called, by the way, Eigenvalue Equation. So from here, I can bring this to the other side. So I have a zero vector on this side. And this thing I can write in this fashion. So what is saying? It's saying that you have this matrix. It's not the original matrix A. You have subtracted a multiple of identity from it to make a new matrix. And then you are acting on some unknowns V to get a zero. So you are trying to you're solving a homogeneous equation. Now, if you want an eigenvector, but by the way, if you look at this equation, this always have a solution, have a trivial solution. What's the trivial solution? If I'm given A, I can choose any lambda. This equation can always be satisfied for some V. What would be that V? So if I just choose V is equal to zero vector, because anything multiplied with zero just gives you zero. So V is equal to zero is always a solution. But we don't call it the eigenvector. This is not called an eigenvector. And lambda would not be an eigenvalue, because this is solved for any lambda. It's a very uninteresting thing. It's a trivial thing. So you want non-trivial solution. So in this definition, I should write, you say V is an eigenvector of A if V is not zero. It's not a zero vector, it's something else. Now, if I come back to this equation, I want a solution of a homogeneous equation. I know that if, let's call this vector, this matrix B, so it is this equation. If B inverse exists, then what would happen? Then you will have, we have done it many times, but let me write it again. You can multiply from the left by B inverse. With the zero vector, it still becomes zero, and this becomes 1. So you get necessarily that V is equal to 0. So this is what we had learned, that if I look at this equation, a homogeneous equation, this one, it has only trivial solutions if B has an inverse. And it can have non-trivial solution if B does not have an inverse. So we are looking for non-trivial solution. So for an eigenvector to exist, for this given lambda, you will have to have that B inverse does not exist. That B is not invertible. So what's that condition? How do you know, how do you check quickly that B is not invertible? Well, you can just compute the determinant. If it's not invertible, determinant of B must be 0. So that means eigenvector with eigenvalue lambda will exist if determinant of this your original matrix whose eigenvalues you're trying to find minus lambda I, you construct this matrix, is 0. This is called the characteristic equation. I don't know why people just keep inventing names. It's just given a name. Now you may imagine that to check if you have an eigenvalue lambda with a corresponding eigenvector, you will have to run through the whole real line. How would you check it? Because this lambda could be anything. How would you check it for all the different real numbers? Well, that's not what you do. You usually, typically what you do is you take this to be an unknown as well. Lambda is an unknown. And when you compute this determinant with an unknown lambda, you get a polynomial in lambda. Because what you have some linear relations and then you are multiplying them. So you construct polynomial. And what would be the degree of polynomial? Is n. If you have a 3 by 3 polynomial, a 3 by 3 matrix, your polynomial will have degree 3. If you have 2 by 2 matrix, it will have degree 2. So then you get a polynomial equation in lambda, and you just solve it to get values, allowed values of lambda. So not all lambdas will be eigenvalues. Typically, if you have a third degree polynomial, you will have only 3 solutions. If you have a 2 degree polynomial, you will have only 2 solutions, and so on. So for an n by n matrix, you can have only n possible solutions of the characteristic equation. So only n eigenvalues. But there is an issue that these eigenvalues, when you say n, some polynomials, when you count this, how many solutions you have of a polynomial, this is probably you haven't learned it. Maybe you do it in high school, that how to count how many solutions a polynomial will have. But you can just take it as a fact, a mathematical theorem, that a degree n polynomial has n solutions. But some of them may be repeated. So when you say that you have n eigenvalues, some of those eigenvalues may be repeated. So you may have, for example, that eigenvalue of a 3 by 3 are 1, 1, and minus 1. So you may be tempted to say that you have only 2, but you really want to say that you have repeated solution because you will have 2 linearly independent eigenvectors corresponding to these repeated values. With each eigenvalue, you will have an eigenvector which will be linearly independent to the other eigenvectors you get for the other eigenvalues. And for repeated values, you will get 2 linearly independent eigenvectors. So that's why you want to count it in the proper fashion. So there's this subtlety that you can have repeated eigenvalues. But there is another problem. Polynomials have n solutions in complex numbers. That you are guaranteed that you will have n solutions, but it's not guaranteed that all n of them will be real. Some of them have real solutions, but some of them have complex solutions. So these eigenvalues may very well be complex. But if they turn out to be complex now, then you have 2 choices. So far we have been sticking with only real numbers. We have been playing only with real numbers. So 2 choices. You just accept the real ones, or you can expand your field. By field, I mean expand the number system which you are using, and just accept that I'm gonna play with complex numbers as well. Then your matrix, starting matrix, may be real. So these may be real entries, but in the eigenvector, in this vector, you may have complex entries, because you generate these complex eigenvalues. So your vectors, they will now not be real vectors, they will be living in a vector space. So these are the vectors. If you take 2 vectors, now you don't only multiply them with real numbers, you make their linear combinations where these numbers a, b belong to the complex plane, to the complex number system. So you allow linear combinations not only with real numbers but with complex numbers. So we will have to consider this, and once we do it, we can find all the eigenvectors and eigenvalues. Should I do an example? Just cook up something and do an example. So let's consider this matrix and find its eigenvalues. So you have to do this. So you get 1 minus lambda, minus 1, minus 1, 1 minus lambda. And now you take the determinant of it. So it's 1 minus lambda square minus minus 1 square and put it equal to 0. So what do you get? Lambda square plus 1 minus 2 lambda minus 1. Lambda square plus 1 minus 2 lambda minus 1 is equal to 0. So you got this cancel and you have got lambda minus 2 is 0. So in this case you have two real roots. Lambda is 0 or lambda is equal to 2. So these are, since it's a 2 by 2 matrix, you should have only two eigenvalues, and these are the two eigenvalues. And then you can find the eigenvectors by plugging these eigenvalues back in. Now you just assume that there is some vector, you know, that which is reproduced with an eigenvalue 0. But what does this mean? The vector itself is not 0, but the eigenvalue is 0. So on the right hand side you get the 0. So in other words, this vector is killed by your matrix. Now it's just a matter of solving this 2 by 2 system. So a minus b is 0 and minus a plus b is 0. So all it gives you is a is equal to b. So any vector, that's the only condition. Any vector which is of this form will be an eigenvector, will be killed. You can check it. So let's take this 2, 2. You get 2 minus 2, minus 2 plus 2, 0. Similarly, I have the other eigenvalue. Let's find the eigenvector corresponding to that. 2 times AB. So I get A minus B is equal to 2A and minus A plus B is equal to 2B. So this means that this equation gives me A is equal to minus B. And the other equation also gives you exactly same. That will always happen. You will have a one-dimensional freedom in choosing your vectors, eigenvectors. They will always be able to, you will always be able to scale them by a number. So the vectors are, in this case, are of this form. Or in other words, 1 minus 1 or 3 minus 3. So let's check. If I check, let's check this one. 1 minus 1. What do I get? I get 1 plus 1 minus 1 minus 1. So the vector I got is 2 minus 2, but this is just 2 times 1 minus 1. So you see that the vector is being reproduced multiplied by your eigenvalue. So any question about this? Let me stop here.